Good morning, students. So today we solve or we prove important recurrence relations. Recurrence formulae. Okay, so these are very important from the examination point of view. So the first one we prove that n plus 1 into Pn plus 1 of x equal to 2n plus 1 into x into Pn of x minus n into Pn minus 1 of x. So this is first one we prove. Okay, so proof. So we know that by generating function formula, okay, by generating function formula, so which we have derived in the last class. So we have 1 minus 2xz plus z square raised to minus 1 by 2 is equal to summation from n is equal to 0 to infinity Pn of x into z raised to n. So this is by generating formula. Now what we do? We differentiate both sides. Differentiating with respect to z, both sides. So we differentiate this partially with respect to z and this also partially with respect to z, keeping x constant. Okay, so now what we obtain? So this is equal to, now differentiation of this is minus 1 by 2 1 minus 2xz plus z square raised to minus 3 by 2 into bracket differentiation of this with respect to z minus 2x then plus 2z, which is equal to summation from n is equal to 0 to infinity. Now differentiation of this z raised to n, so this Pn of x is constant, so n into z raised to n minus 1 we obtain. Okay, so now this is equal to, so here this is minus 1 by 2 into 1 minus 2xz plus z square raised to minus 3 by 2. Now here we take 2 common, 2 into this becomes z minus x. Now this is n summation from n is equal to, sorry, I write n here only, so n into Pn of x z raised to n minus 1. Now here this 2 then 2 get cancelled, 2 and 2 get cancelled, so which gives minus 1 minus 2xz plus z square raised to minus 3 by 2, okay, into z minus x which is equal to so n into summation from n is equal to 0 to infinity n into Pn of x into z raised to n minus 1 Okay, so this is the given z raised to n minus 1. Now here this minus can be multiplied with this. So this can be written as 1 minus 2xz plus z square raised to minus 3 by 2. Again this becomes x minus z, summation from n is equal to 0 to infinity n into Pn of x into z raised to n minus 1. Z raised to n minus 1. Okay. Okay, so now I will write this as 1 minus 2xz plus z square raised to minus 1 by 2 into 1 minus 2xz plus z square raised to minus 1, because this minus 3 by 2 can be split as this is a raised to m can be written as a raised to m into a raised to n. So 1 minus 2xz plus z square raised to minus 1 by 2 and into 1 minus 2xz plus z square raised to minus 1, so that bases are same. When you add these two, again you will get the same thing here. So this is x minus z, which is equal to summation from n is equal to 0 to infinity n into Pn of x z raised to n minus 1. So now multiplying both sides. Multiply both sides with 1 minus 2xz plus z square. Multiply both sides with this term. So then what happened? If you multiply this with this one, so here raised to minus 1 and this is raised to plus 1, both will get cancel each other, and here this is multiplied with this. Okay, so we get so 1 minus 2xz plus z square raised to minus 1 by 2. Okay, raised to minus 1 by 2, this will cancel each other, into x minus z equal to okay. Now here this is multiplied equal to 1 minus 2xz plus z square, summation from n is equal to 0 to infinity n into Pn of x into z raised to n minus 1, right? So this is, when you multiply this with this. Okay, so now from equation 1, so call this equation 1, which is the, let us call this equation as 1. Okay, so this will not come each other. So this is equation 1. Okay, this is equation 1. Now from this equation 1, this is equal to what? N is equal to summation from n is equal to 0 to infinity Pn of x into z raised to n. Okay, so therefore here this is equal to, from equation 1 we have this is nothing but summation from n is equal to 0 to infinity n is equal to 0 to infinity. The equation is Pn of x into z raised to n, and this one as it is x minus z, which is equal to, this one is same, 1 minus 2x plus z square, summation from n is equal to 0 to infinity n into Pn of x z raised to n minus 1. Now multiplying these two, okay, so which gives, multiplying these two terms, which gives summation from n is equal to 0 to infinity x into Pn of x into z raised to n, then minus this into this. Okay, this into this, that is summation from n is equal to 0 to infinity Pn of x into here z into z raised to n, so it becomes z raised to n plus 1, z raised to n plus 1. So similarly we multiply these two terms, each and every term. So first 1 into this one, next this into this one, then plus this into this one, right? So first 1 into this one, so which is equal to summation from n is equal to 0 to infinity. So n into Pn of x z raised to n minus 1. Next this into this, so minus summation from n is equal to 0 to infinity to n x into Pn of x into z raised to, here plus 1 and minus 1, z raised to only n, z raised to n. Okay. Next plus summation from n is equal to 0 to infinity, this into this, so n into Pn of x z square into z raised to n minus 1, so minus 1 plus 2, so it becomes plus 1, so z raised to n plus 1, z raised to n plus 1. So after multiplication and simplifying we get this equation. Okay. So next is equating the coefficient of z raised to n on both the sides. Okay. So what we do next is equating the coefficient of z raised to n on both sides. Okay, so equating the coefficient of z raised to n. So here there is a z raised to n term. Okay, so its coefficient is x raised to n Pn of x, right? So one we got. So first one is x raised to n into Pn of x. Okay, next where is z raised to n? We have to search for that first. Okay, so here it is z raised to n plus 1. There is no z raised to n term, and here also there is no z raised to n term, and here it is z raised to n. So minus 2nx into Pn of x, right? So when you will come this side, it becomes plus 2nx. So 2nx into Pn of x into Pn of x, 2nx into Pn of x. Okay, then next z raised to n, we have to search for z raised to n. So equating the coefficient of z raised to n on both the sides. Okay, so here okay, now here wherever z raised to n, here 1 will get, and another one is here if you replace n divided by n minus 1. Okay, if n varies from 0 to infinity, right? So therefore if you replace here n is equal to n minus 1. Okay, here n is equal to n minus 1 in this, so plus 1 minus 1 get cancelled, so this becomes z raised to n, and here also you replace n by n minus 1, so it is Pn minus 1 of x. Okay, so this is the coefficient of z raised to n. So one more will get Pn minus 1 of x, Pn minus 1 of x, right here. Then next here, if you replace n by n plus 1, if you replace in this n by n plus 1, then plus 1 minus 1 get cancelled, again you will get this as z raised to n, and its coefficient is n. If you replace n by n plus 1, here also you replace n by n plus 1, and here also you replace n by n plus 1. So when you replace n by n plus 1, plus 1 minus 1 get cancelled, and it becomes z raised to n. Then its coefficient is n plus 1 into Pn plus 1 of x. So when it comes to this side, it becomes minus. Okay, so which is equal to minus of n plus 1 into Pn plus 1 of x, Pn plus 1 of x. Okay, so next here we took this one. Next here, if again you replace n by n minus 1, n by n minus 1, then plus 1 minus 1 get cancelled. Here n minus 1 into Pn minus 1 of x. So then minus n minus 1 into Pn minus 1 of x equal to 0. Okay, so now collecting the, or taking the common term, taking the same terms common. So where it comes, so here this is x, so x, then taking Pn of x common, taking Pn of x common wherever it is 2 times appears. So one Pn of x is here and one Pn of x is here. You can take x into Pn of x. So I'll take x into Pn of x, then we'll get 2n plus 1 into x into Pn of x. Okay, so next from this side, this term, I take minus of Pn minus 1 of x, and in bracket I left with 1 plus n minus 1. Okay, 1 plus n minus 1, and then here I write this one as it is, n plus 1 into Pn plus 1 of x equal to 0. So here plus 1 minus 1 get cancelled, or it is 2n plus 1 into x into Pn of x, x into Pn of x, okay, then is equal to, okay, is equal to minus of n plus 1 into Pn plus 1 of x, and here it is minus n into Pn minus 1 of x equal to 0. Okay, so now what we need, we should bring the given equation in terms of the given one. So take this one on that side, so this becomes n plus 1 Pn plus 1 of x, okay, is equal to, so this is 2n plus 1 x into Pn of x minus n into Pn minus 1 of x. So this is the first one. Okay, so this is the first relation or first recurrence relation. This is the first recurrence relation. Okay, so similarly we prove the second one. So second one we have, prove that n into Pn of x is equal to x into Pn dash of x minus Pn minus 1 dash of x. N into Pn of x equal to x into Pn dash of x minus Pn minus 1 dash of x. Again we use the same relation. Again we use the same generating formula. So proof so by generating formula, so what we have, 1 minus 2xz plus z square raised to minus 1 by 2 equal to n into 0 to infinity Pn of x into z raised to n, Pn of x into z raised to n, right? So this is equation 1 we write. Next what we do, differentiating 1 with respect to z. Differentiating equation 1 with respect to z. So what we get, so minus 1 by 2 into 1 minus 2xz plus z square raised to minus 3 by 2 into bracket minus 2x plus 2z equal to summation from n is equal to 0 to infinity n into Pn of x z raised to n minus 1. So this is we obtain by differentiating with respect to z. Again by taking 2 common and cancelling each other as we done in the last problem. So that is we get 1 minus or x minus z minus x minus z. Okay, this gives this gives z minus x, so it becomes x minus z into bracket 1 minus 2xz into z square raised to minus 3 by 2. So taking 2 common from this, 2 to get cancelled, then multiply this minus with this, so minus minus becomes plus, and this is minus, so x minus z, this is same as, now this is equal to summation from n is equal to 0 to infinity n into Pn of x z raised to n minus 1, z raised to n minus 1. So this is equation 2, this is equation 2. Okay, so now again differentiating equation 1. Differentiating 1 with respect to x now, with respect to x. Okay, so differentiate again same equation with respect to x. We get this is minus 1 by 2 1 minus 2xz plus z square raised to minus 3 by 2 into differentiation of this with respect to x. So this is 0, then minus 2z, then this is again 0, which is equal to summation from n is equal to 0 to infinity. Now this is Pn dash of x differentiating with respect to x. Now z raised to n as it is. Z raised to n as it is. Okay, now again here this 2 and 2 get cancelled and minus minus becomes multiplied, so which implies z into 1 minus 2xz plus z square raised to minus 3 by 2, because minus into minus becomes plus, this 2 and 2 get cancelled, z into 1 minus 2xz plus z square raised to minus 3 by 2 is equal to summation from n is equal to 0 to infinity Pn dash of x into z raised to n. Okay, okay, so now multiply both sides with x minus z, both sides, so which gives z into x minus z into 1 minus 2xz plus z square raised to minus 3 by 2, 1 minus 2xz plus z square raised to 3 by 2, which is equal to x minus z into n is equal to 0 to infinity Pn dash of x into z raised to n. Okay, so this is obtained by multiplying with x minus z on both the sides. Okay, so now call this equation call this equation as 3. Call this equation as 3. Okay, now from 2 and 3, so this is equation 2. So here it is, what is x minus z into 1 minus 2xz plus z square raised to minus 3 by 2 is equal to this much. Okay, next again from equation 3, again in that 3 we have x minus z into 1 minus 2xz raised to minus 3 by 2 is equal to this much. Okay, so now from 2 and 3, so we substitute this value of is equal to this in this equation here. Okay, so from 2 and 3, so here this one is common, x minus z 1 minus 2xz plus z square raised to minus 3 by 2, and in equation 2 we have this one. So substituting this value of is equal to this in this equation, so here we have that term. Okay, so from 2 and 3 we get, from 2 and 3 we get z into summation from n is equal to 0 to infinity n into z raised to n minus 1 Pn of x is equal to x minus z into summation from n is equal to 0 to infinity z raised to n into Pn dash of x. So now again equating the coefficient of z raised to n both sides. So we get here equating the coefficient of z raised to n. So when we multiply z with this term, z plus z get cancelled, and you will get this as n into Pn of x, which is equal to, and here also you multiply this z raised to n, we get x into Pn dash of x minus, again you multiply this with z raised to n minus 1, it will give. So z raised to n minus 1 means when you substitute n is equal to n minus n plus 1. Okay, so this is z raised to n plus 1. When you substitute n is equal to n minus 1, then it changes Pn minus 1 dash of x. So it is equal to Pn minus 1 dash of x. So this is the second relation. So this is the second relation. Okay, similarly we have totally we have 6 relations, and out of that we have proved only 2 relations. So in the next class we prove other relations. Okay, so with this I conclude this class. Thank you.